We're going to take a look at another addition rule, and this one is going to be this rule here. The probability of A or B occurring is simply the probability of A plus the probability of B. Now, we're not going to do this. In the last section, we subtracted off the probability of A and B, and that was the general probability rule. Now, we are going to omit this because we are going to assume now that the events A and B are mutually exclusive. Here's what we mean. Two events, A and B, these are going to be mutually exclusive if when one of them occurs, the other one cannot. And just mathematically, that means that the intersection is empty. That's the empty set. That's the set with no elements. So there's nothing common, right? Nothing common between these two events. So if one of them occurs, the other one cannot. Here's a simple example. Toss a die once. Let A be the event that a 3 shows up on the top face, and B be the event a 4 shows up. Now, I'm going to claim that A and B are mutually exclusive. Right? Does that make sense? If a 3 shows up, right, you toss a die once. If a 3 is on the top face, it can't be a 4 at the same time. Or if a 4 shows up, it can't be a 3 at the same time. We draw a Venn diagram for this. It would look like this. Here's a set of all possibilities. Here's the event A, and here's the event B, and there's nothing in common. A intersect B is empty. These two events are mutually exclusive. And while we're drawing pictures, here's a quick note for an important concept. If you have an event here, like here's A, outside of A, this would be A complement. Right now, you're either inside A or you're outside A. You can't be in both places. So what we have then is this. If you take the probability of A and add the probability of not A, you have to get 1. Or, with a little bit of algebra, what's the probability that A does not occur? That's 1 minus the probability that A does occur. Or, if you like, what's the probability that A occurs? It's 1 minus the probability that it does not occur. Let's do an example. Suppose you draw a deck from the standard deck of 52 cards, and first of all, find the probability of getting a 4 or a 5. All right, now I'm going to claim that 4 and 5, these events are mutually exclusive. Because if you draw a 4, there's no way it can be a 5 at the same time. So the probability of getting a 4 or a 5, or if you want to use our notation like that, this would just be the probability of choosing a 4 plus the probability of a 5. Now getting a 4, there's 4 of hearts, 4 of diamonds, 4 of spades, 4 of clubs. There's 4 4s out of 52. There's 5 5s in that deck. So this is going to be 9 out of 52. Now, probability of getting a queen or a club. Well, these are not mutually exclusive because there is a queen of clubs. All right, so these are not mutually exclusive. So what are we going to have here? This is going to be the probability of getting a queen or a club. This is going to be the probability of getting a queen plus the probability of getting a club minus the probability of getting a queen and, well, a queen. Okay, I'll do it in order here. Doesn't matter. A queen and a club. So there's 4 queens in the deck, so 4 out of 52. Plus there's, now every suit has 13 cards in it, so there's 13 clubs out of 52. Minus, but there's only 1 queen of clubs. Right, so we're going to get 4 plus 13 minus 1 over 52. So we're going to get what? 16 over 52.